Continuing with the earlier lecture, where we have just started the solution of ODE using the Fourier transform. Let us do one or two more problems, so that you can better understand how to one can find out the solution of ODE using the Fourier transform and its properties. Like you have seen, initially I am taking the Fourier transform on both sides. Using the property, I am getting some equation in terms of y of alpha. Then I am taking inverse Fourier transform. There I may have to use the convolution theorem. It is better to use the convolution theorem, and from there I will get the solution. So, now let us consider this example. d2y dt square plus 6 dy dt plus 5y equals delta t, where obviously delta t is the Dirac delta function, where delta t is Dirac delta function, and that is the reason we have done earlier the Dirac, what is the Fourier transform of Dirac delta function, what is the Fourier transform of the Heaviside unit step function, all these things we have done earlier. Now, you take the Fourier transform on both sides, take Fourier transform on both sides. If I take Fourier transform on both sides, what I will obtain? Fourier transform of d2y dt square plus 6 into Fourier transform of dy dt plus 5 into Fourier transform of y. This is equals to Fourier transform of Dirac delta function. This I will obtain. And if you recall, you already we have done it, that Fourier transform of y n x is minus I alpha whole to the power n into y x. So, if I use this formula, then Fourier transform of d2y dt square I can write down minus I alpha whole square into y of alpha, say, where y of alpha is nothing but Fourier transform of y t plus 6 into Fourier transform of dy dt will be minus I alpha into y of alpha plus 5 into Fourier transform of y, which is nothing but y alpha. And if you recall, Fourier transform of Dirac delta function, which again we have done earlier, which is nothing but 1 by root 2 pi. So, I am getting this equation after taking Fourier transform on both sides of the given equation. So, that I can just take the commons, it will be minus alpha square minus 6 I alpha plus 5 of y alpha into y alpha, this is equals to 1 by root 2 pi. So, that you can write down y alpha equals to 1 by root 2 pi into this. If I take on that side, y alpha will be equals to 1 by root 2 pi into 1 by alpha square plus 6 I alpha minus 1, 6 I alpha minus 5. So, that this is minus I square minus alpha square. So, minus sign should come over here, and if I break this thing, this ultimately I will obtain 1 by 4 into root over 2 by pi into 1 by I alpha minus 5 minus 1 by I alpha minus 1. If I break it into two parts, I will obtain 1 by 4 root 2 pi into this. Therefore, from here I can write down, and this equals, you can write down Fourier transform of y t equals 1 by 4 into root over 2 by pi into 1 by 1 minus I alpha minus 1 by 5 minus I alpha. Once I am obtaining this, y t I can obtain by taking the inverse Fourier transform. Y t will be equals to 1 by 4 into root over 2 by pi into Fourier inverse of 1 by 1 minus I alpha minus Fourier inverse of 1 by 5 minus I alpha. So, now basically this is equation 1, and once I know what is the value of the Fourier inverse of 1 by 1 minus I alpha or Fourier inverse of 1 by 5 minus I alpha, I can always tell what will be the yt. So, to find out the value of this Fourier inverse of 1 by I minus alpha, let us start with this integral e power minus at into ht, where again I am repeating ht is nothing but the unit Heaviside function. So, Fourier transform of e power minus at into ht, from the definition this you can write down 1 by root 2 pi minus infinity to infinity e power minus at ht into e power I alpha t dt. You can write down this thing e power I alpha t into dt. This equals 1 by root 2 pi. Your ht, as I told you, it is 1 for t greater than 0 and 0 for t less than 0, this function ht, which is Heaviside unit step function. So, that minus infinity to infinity now will be boils down to 0 to infinity, and value of this ht, this will be equals to 1. For this in 0 to infinity and minus infinity to 0, value of ht is 0. So, that this equals, you can write down e power minus a minus I alpha into t into dt. So, please note that again I am repeating ht equals 1 for t greater than 0 and it is 0 for t less than 0. Once you have obtained this thing, so this I can evaluate the integral 1 by root 2 pi into this will be e power, if I evaluate the integral, minus a minus I alpha into t by minus a minus I alpha. This will come where the limit will be from 0 to infinity. For infinity the value will become 0. For this one, for 0 it will become 1 by a minus I alpha. So, that your result will be 1 by root 2 pi into 1 by a minus I alpha. So, once I have obtained this Fourier transform of e power minus at into ht, this I am seeing that it is 1 by root 2 pi into 1 by a minus I alpha. So, that from here you can write down Fourier's inverse Fourier transform 1 by a minus I alpha is nothing but root 2 pi will go there, root over 2 by pi e power minus at into h of t, where h t has been defined over here, where h t has been defined over here. So, once I have obtained this one, the other one also I can, once I am obtaining this. So, let me write down, rewrite again, that would be easier. I started with Fourier transform of a minus I alpha. This is equals to root over 2 by pi into e power minus at into h of t. Now, you put a equals 1 here. So, that you will obtain Fourier inverse of 1 by 1 minus I alpha. This will be equals to then root over 2 by pi e power minus t into h of t. And if I put a equals 5 over here, then you can obtain the value of the inverse of the second function, that is 5 minus I alpha. That is the reason we developed the generic one and we obtained what is the Fourier inverse of 1 by a minus I alpha, which is this one. So, this you can write down root over 2 by pi into e power minus 5 t, a t was there, into h of t, where h of t is the unit Heaviside function. So, therefore, if I substitute now these two values in 1, from 1 I can write down your yt is nothing but 1 by 4 into root over 2 by pi into these two values, that is root over 2 by pi e power minus t into h of t minus root over 2 by pi e power minus 5t into h of t. So that here root 2 pi, if I take common, it will go out, it will be cancelled, h t I can bring it outside. So, it will be h t by 4 into e power minus t minus e power minus 5t. So, please recall this thing, that using this form I am getting the Fourier inverse, I am trying to find out, and once I am finding out the Fourier inverse, then by some way I have to find this value of Fourier inverse. Once I obtain the Fourier inverse of 1 by 1 minus I alpha and Fourier inverse of 1 by 5 minus I alpha, then I can tell what is the value of h t. That is, h t equals h t by 4 into e power minus t minus e power minus 5 t. This actually you can tell for t greater than 0, it will be equals to 1 by 4 into e power minus t into e power minus 5 t, and for t less than 0 the value will be 0. So, like this way we can solve one ODE. So, let us take one more example and then we will go to the next topics. So, next example, say d2y d square dt square plus 3 dy dt plus 2y. This is equals, I have given e power minus 3t into h t. This already we have done. What is the Fourier transform? So, where h t is the Heaviside unit step function, as we have mentioned earlier, h t is the Heaviside unit step function where h t equals 1 for t greater than 0 and 0 for t less than 0. So, if I take now the Fourier transform on both sides of the given equation, following the similar process, you will obtain Fourier transform of d2y dt square plus Fourier transform of dy dt plus 2 into Fourier transform of y. This is equals to Fourier transform of e power minus 3t into Heaviside unit step function, that is h t. So, this Fourier transform of d2y dt square minus I alpha whole square into y of alpha, where y alpha again like earlier problems is the Fourier transform of y t plus Fourier transform of dy dt will be 3 will come here, 3 dy dt is there. So, it will be 3 into Fourier transform of dy dt. So, plus 3 into minus I alpha into y alpha plus 2 into y alpha Fourier transform of y, and this value we have done already 1 by root 2 pi into 1 by 3 minus I alpha. So, this Fourier transform of e power minus 3t into h t, this we have done already using that property. We are writing this is equals 1 by root 2 pi into 1 by 3 minus I alpha. So, that this you can write down minus alpha square minus 3 I alpha plus 2 of y alpha. This is equals to 1 by root over 2 by pi into 1 by 3 minus I alpha. So, you can write down your I alpha equals minus 1 by root 2 pi into 1 by 3 minus I alpha you will get into 1 by alpha square plus 3 I alpha minus 2, minus we have taken common. So, this again I have to break it into two parts. This integral 1 by 3 minus this portion 1 by 3 minus I alpha into alpha square plus 3 I alpha minus 2. This I have to break it using componendo and dividendo. I am not showing it. So, directly I am writing Fourier transform of y t. This is equals to minus 1 by root 2 pi. You should check it of your own whether I have written it correctly or not, minus half into 3 minus I alpha plus 1 by twice I into alpha plus I. These things you have done earlier. So, I am not showing it, minus 1 by I into alpha plus twice I. So, once I am breaking it, I will obtain this. This term basically divided can be broken into like this. So, that Fourier transform of y t, once I am getting this, from here you can write down y t equals, using inverse Fourier transform, 1 by root 2 pi minus, we can take outside, 1 by root 2 pi half into Fourier inverse of 1 by 3 minus I alpha minus 1 by 2 I Fourier inverse of 1 by alpha plus I plus 1 by I into Fourier inverse of 1 by alpha plus twice I. And if you note, once I am writing this, Fourier inverse of 1 by a plus I alpha, this particular form already we have done it in the last example. What is the Fourier inverse of this function? That already we have done. So, I am directly writing that part, I will not use it again. So, this will be half into root over 2 by pi, this will be e power minus 3 t into h of t. The Fourier inverse of this, please note that you should check it of your own again, plus half into this, I will write down Fourier inverse of 1 by 1 minus I alpha in this form, because I know a minus I alpha, and similarly plus 1 by I if I take it common. So, Fourier inverse of this we can write down I squared. So, 2 minus I alpha. So, once I am writing it in the form of a minus I alpha, directly I can put the values. So, this is equals to 1 by root over pi, 2 by pi half into root over 2 by pi e power minus 3 t into h t plus half into root over 2 by pi. Here it will be a is 1 e power minus t into h t minus root over 2 by pi. Here your a is 2. So, e power minus 2 t into h t. So, using one example, I am finding out the Fourier inverse of these functions. So, now if I take the root 2 pi outside, that will be going out, and after simplification you can write down half into e power minus 3 t plus e power minus t minus 2 into e power minus 2 t into h of t. So, the solution becomes this thing, that y t equals half into e power minus 3 t plus e power minus t minus 2 into e power minus 2 t into h t. So, I hope it is clear to you now how to find out the solution of ODE using the Fourier transform. Now, let us go to the next topics, that is application of Fourier transform to integral equations. That is, whenever integral equations are provided to us or an integral equation is given to us, we want to find out the solution of that integral equation using the Fourier transform. Let us take the example directly. Find the solution of the integral equation 0 to infinity f x cos of t x dx equals e to the power minus t. So, from here what I have to find out? I have to find out what is the value of f x. Please note this one. I want to find out the value of f x from here. So, if we do it, the equation is given as 0 to infinity f x into cos of t x dx, this is equals to e power minus t. Now, multiply both side by root over pi by 2, sorry, not pi by 2, but root over 2 by pi. If I multiply both sides by root over 2 by pi, I will obtain 0 to infinity f x into cos of t x dx. This is equals root over 2 by pi e power minus t. So, once I am multiplying by root over 2 by pi on both sides of the given equation, then I will obtain root over 2 by pi 0 to infinity f x cos of t x dx. Whether this integral is familiar to you? If you remember, this integral is nothing but the Fourier cosine transform of f x, because from definition Fourier cosine transform of f x is nothing but root over 2 by pi 0 to infinity f x cos of t x dx. So, I can write it capital F c of t, this one, this integral. This is f c of t, this is nothing but the Fourier cosine transform of this, and this is equals to root over 2 by pi e power minus t. So, once I am obtaining Fourier cosine transform of a function, then I can use the inversion formula to derive what is small f x, because I know using inversion Fourier cosine inverse I can write down what is my small f x. So, once I have this particular one, that Fourier cosine transform of t is known as a function of t, that is root over 2 by pi e power minus t. From here I can write down f x equals root over 2 by pi 0 to infinity Fourier cosine transform of t into cos of t x dt. So, once I am obtaining this, I know what is the Fourier cosine transform of this. So, if I substitute the value of Fourier cosine transform of t equals f x equals root over 2 by pi e power minus t. So, this integral will be reduced to 2 by pi 0 to infinity e power minus t into cos of t x dt. So, effectively I have been given this integral, you see, multiplying both sides I am using just Fourier, I am getting the Fourier cosine transform. Then using the inverse Fourier cosine transform, I can tell what is f x. So, only thing I have to do it now, I have to evaluate this integral 0 to infinity e power minus t cos of t x dt, and then I can tell that what will be the value of f x. So, let us evaluate the integral now. Your I is nothing but 0 to infinity e power minus t into cos of t x dt. So, now you can use the integration by parts to evaluate the integral. So, the first one will be e power minus t cos t x will become sin t x by x, where your t will vary from 0 to infinity plus 1 by x 0 to infinity e power minus t into sin of t x into dt. So, this I am keeping as it is at present, e power minus t sin t x by x, where t lies between 0 to infinity. For the second integral, again use the integration by parts. So, that actually I can get back the original integration, that is 0 to infinity e power minus t cos t x. So, if I do that one, I will obtain minus will come e power minus t into cos of t x by x square, t equals 0 to infinity, I will obtain minus 1 by x square 0 to infinity e power minus t into cos of t x dt. So, therefore, your this portion is nothing by I, this portion is I, and once this is I and I am bringing that one on that side. So, that it will be 1 plus 1 by x square into I. So, that your result, in the result directly I can write down your I will be equals to x of sin t x, just I am simplifying this to minus cos t x into e power minus t divided by this 1 plus x square will come, and the limit will be from 0 to infinity. So, once I am getting this, your I is this one. Let me rewrite this thing, it would be better. Your I equals you are obtaining as x sin t x minus cos t x into e power minus t divided by 1 plus x square, t lies between 0 to infinity. So, that once t is 0, it will be 1, and for infinity it will become 0. So, value you will obtain as nothing but 1 by 1 plus x square. For 0, sin term will vanish, cos term will be 1, minus was there. So, it will be plus. So, I equals 1 by 1 plus x square. So, therefore, what was your I? I was nothing but the given integral 0 to infinity e power minus t into cos of t x dt. This was the integral and its value is this. So, your f x is what? F x is root over 2 by pi. Root over 2 by pi will come into this integral 0 to infinity e power minus t into cos of t x dt. And this value already you know, that is 1 by 1 plus x square. So, that you can obtain the result 1 by 1 plus x square into this quantity. So, let us see quickly over here. The function was this, and multiplying both sides on the given equation, we are obtaining root over 2 by pi 0 to infinity f x cos t x dx equals root over 2 by pi e power minus t, and the left hand side integration is nothing but the Fourier cosine transform of f x. From the definition of Fourier cosine transform, we can say left hand side integral is nothing but Fourier cosine transform of this. So, it will be this one. So, Fourier cosine transform of t equals root over 2 by pi e power minus t. So, that if you take the inverse Fourier transform, always you can obtain what is your f x. So, your f x is root over 2 by pi 0 to infinity Fourier cosine transform of x into cos of x t, and you know the value of Fourier cosine transform of t is root over 2 by pi e power minus t. So, if I substitute the value of Fourier cosine transform of x, I will obtain this integral. So, only thing remaining is I have to evaluate the integral. So, I am assuming I equals 0 to infinity this is standard one. So, I am using integration by parts. Again on the second integral, again I am using integration by parts. So, that if you see this third one, this third integration is nothing but I. So, if I take it back on that side, I can write down I equals this limiting value, which is nothing but 1 by 1 plus x square, and from here I can write down f x equals root 2 by pi into 1 plus x square. 2 by pi into 1 plus x square is the given result. Earlier I told it was root over 2 by pi, but it is not root over 2 by pi, because root over 2 by pi into root over 2 by pi came and it became the 2 by pi. So, final result is f x equals 2 by pi into 1 plus x square.